So, next is the turbulent length scales. Okay, there are 4 length scales which are commonly defined and used. They are the first one is called the characteristic dimension of the flow itself. Okay, so that is the biggest this length scale what we can have. So, the dimension of the flow, please understand the dimension of the flow itself. For example, in a boundary layer, the boundary layer thickness can be the characteristic dimension we can use. Okay, turbulent boundary layer thickness del T. So, if we go back here, yeah, this is the turbulent boundary layer thickness delta T, that will be a characteristic dimension for us. Okay, so that will be the first one, which is the characteristic dimension of the flow, or we just call it a macro scale, capital L, macro scale. So, that will be the characteristic dimension of the particular flow. So, it may be internal flow, external flow, anything. So, for the characteristic dimension associated with that is called the macro scale. The next 3 are turbulent scales, which will basically depend on the turbulence, intensity and other things. So, first we define what is called the largest turbulent scale, which is called integral scale, L suffix 0, integral scale. So, this is also called, because this is the maximum possible length scale within the turbulence. So, we say this is called turbulence macro scale. So, when you consolidate all the eddies together and see what will be the maximum dimension of in the domain. So, that will be the macro scale or the characteristic dimension of the flow, that is the first scale, the largest. Okay. Second one is the integral scale, which is also called turbulent macro scale. Turbulent macro scale is nothing but the large size turbulent eddy, that will be represented by this. Then comes the micro scale, which is called Taylor's micro scale, L suffix lambda, Taylor's micro scale, and the smallest scale is called Kolmogorov micro scale, L suffix k. So, that these are the 4 things, and out of which the 2, 3, 4 are the representative of the eddy sizes in the turbulent flow. Okay, so these are the 4 time scales, length scales: macro scale, characteristic dimension of the flow, then integral scale, which is the largest eddy size in the this turbulent macro scale it is called. Then the Taylor's micro scale, which represents the medium, like a medium level, lesser than the integral scale basically. Then the smallest length scale is called the Kolmogorov scale, micro scale, LK. So, as I told you, the macro scale is nothing but the largest length scale in the system or the control volume. If, for example, if you take a jet flow, the width of the jet, okay, half width of the jet, for example, can be taken as the macro scale or the characteristic dimension. And for the pipe flow, the diameter of the pipe itself, so the maximum possible eddy size will be this. So, eddy cannot, this is the flow thing. So, the jet frets to its width. So, the maximum eddy size what we can anticipate here is the width. So, after that there is no jet at all. So, the jet the eddy cannot be larger than that. So, the macro scale normally represents the largest possible eddy size, and it does not talk about the, so since I say macro, it does not talk about the particular flow field like eddy size and so on. But anyway, this is the general thing. So, for example, we can use this for even this length scale can be used for laminar flows also. For example, diameter of the pipe we have used to define the Reynolds number in a pipe flow. Similarly, the jet width, half width, the jet width, etc., we can use as a length scale for the jet. So, this we can also use in the laminar flow, that is the macro scale. Second scale, as I told you, second, third and fourth are specifically to the turbulent eddy size, and this integral scale, which is also called the turbulence macro scale, represents the mean size of the medium to large size eddy, mean size, average size of medium to large size eddy. Okay. So, now please understand that once you go into the turbulence, we cannot just take a particular size of the eddy. So, here we are definite, the macro scale, the flow, the characteristic dimension of the flow, we know that the jet width will be like this based upon Reynolds number, and the pipe diameter is this fixed, everything is fixed, correct. But in this, we again, when you go into turbulence, we have to do some statistics. So the statistics what you do for the integral scale is nothing but the mean size. So you have to take some average of what? The medium to the large eddies which are present in the flow. When you take the average of or mean values of the medium to large, I only take the large eddies to medium size eddies, and take a average value of these sizes, then I get that scale. Okay, now how will you do this? How will you calculate the eddy size? So that is done actually by using what is called correlation coefficient. Okay, see, correlation is nothing but when I do a measurement at see, I can do a measurement using a hot water anemometer at a particular location. Okay, then I get see, for example, I measure the velocity, one of the common velocity, say u with this, so I get u as a function of time. So I now fix the location. Okay, say x1 is the location, x1 is the location in which I put the probe, hot water anemometer, and do the measurement. So now I get time, with time u how it varies. Okay, so this I can do this for the another location x2. So and I get, say, this is my u1t and this may be u2 of t, I get this. Now I can see what will be the relationship between these two. So that is called correlation. When I do, for example, u1 into u2 etc., whether it is cancelling out or it is enhancing, so that will give the correlation. So the correlation is nothing but when I do measurement in two locations as a function of time, at the same instant how these two correlate. So that correlation is what is will tell you the size of the eddies. So if the points are within a particular eddy, it will correlate better. If the points are not within an eddy, it will not correlate. So based upon the correlation, I will decide the size. So when I do this measurement at different x1, x2, etc., I will know what is the medium size eddy, what is the large size eddy, etc. Once I know these correlations, I integrate from the so medium to large size. So actually I do the some particular distance I take and put the probes and take the measurements and try to correlate till which distance I get the correlation, that will decide the mean size. So that if I take, that will correlate the medium to large size eddies. So that scale is called integral time scale. So it is got by integrating the correlation coefficient of velocity fluctuations at two locations at the same time instant. So I get the time data, and at a particular time instant, what is the correlation between this? If the data is within the same eddy, it will correlate better. So that with that I can see this is, so these 2 points are within the same eddy. So I know the dimension of the eddy now, correct? Similarly I go, so if there is no correlation between one point and another point, then these 2 points are not within the same eddy and so on. So some type of meaningful derivations can be done by this measurements, but please understand again we have to do correlations with some statistical procedure. So that is what we try to do this and get the value of the integral scale. Then comes the microscale, which is called Taylor's microscale L suffix lambda. It is an intermediate scale. Okay. So now the largest flow field scale is macro scale, and the next is integral scale, which is the turbulence macro scale, which is actually the average of the size of eddies present in medium to the large size eddies. Then comes the micro scale, which is intermediate scale, which is an intermediate scale, and it is weighted more towards the smaller eddies. So we have medium to large we have covered. So now smaller to smaller eddies we need to cover. So it may small to intermediate. So that range. So it will be weighted more towards smaller, and that means that it will represent the average of the smaller eddies. So we can say average of the smaller eddies. So which is actually defined as the ratio of root mean square value of the velocity fluctuation V dot RMS and the ratio. So this to the mean strain rate. So mean strain rate we can say dVx by dx bar square under square root, something like that. So this may be the mean strain rate. Strain rate is nothing but the derivative of velocity, but whenever you take derivative, normally we take a mean square and take a square root. So that will be the this, so that positive value you can take. So this may be called mean strain rate. Mean means time average. Mean strain rate Okay, now V dot RMS will be nothing but root of V dot square mean. Okay, so this if you take a ratio of this V dot RMS to this strain rate, mean strain rate, you get the Taylor's microscale. So again, please see that when I define the Taylor's the turbulent length scales, like the it is the integral scale L naught or L lambda or L k, we will use only the turbulent quantities like VRMS or correlations between two fluctuating quantities and so on. Okay, so this is the length scale at which the viscous dissipation starts to affect the eddies. Correct, viscous dissipation will start to affect the eddies. That means that there is a energy dissipation away from the smaller eddies. Normally, bigger eddies will take the energy from the free flow, the main flow, and it will shed the eddies to the smaller and smaller eddies. The smallest eddy will dissipate it. The smaller eddies also will start to dissipate it. So that is the thing. So viscous dissipation starts at the to affect the eddies at this scale. Now the smallest length scale is called Kolmogorov scale LK. So that represents the size of the smallest eddy in the flow. Okay, smallest eddy. So how will you do this? How will you calculate it? Basically, it is calculated as a function of kinematic viscosity. So because the viscous dissipation is the largest in this, so viscous effects are predominant in this particular scale. So we use the kinematic viscosity nu, that is mu by rho, dynamic viscosity by density, and the rate of dissipation of turbulent Ke, kinetic energy. So that if I use that, then I get the Kolmogorov scale. So you can see the nu by epsilon naught. This is the rate of dissipation of turbulent kinetic energy. Okay, so this can be written as that the dissipation of turbulent kinetic energy, rate of dissipation of turbulent kinetic energy can be written as 3 by 2 VRMS square divided by the integral scale divided by V dot RMS. So this, if you substitute here, you get the LK. So these are the 4 time scales. The last 3 are exactly the representative of the size of eddies. For example, the integral scale is representative of the mean size of the medium to large eddies. Then the Taylor microscale is the average size of the smaller eddies, and the Kolmogorov scale is the size of the smallest eddy. So based upon the length scales, okay, so using the turbulent length scales and the root mean square value of velocity, so V dot RMS, okay, we get 3 Reynolds numbers defined. Okay, so RE L naught is V dot RMS L by nu. So we actually take the nu value which is molecular kinematic viscosity, so that we use it and define the Reynolds numbers. RE L naught is the Reynolds number defined based upon the integral scale. RE L lambda is that defined upon the Taylor's microscale, and Kolmogorov scales RE L k represent that. The Reynolds number defined based upon the Kolmogorov scale, and now with Reynolds number we can relate the length scales. So for example, the integral length scale L naught by the Kolmogorov length scale Lk is nothing but RE, we can prove this, RE of L naught, correct, which is defined here, that is the integral scale based RE value to the power of 3 by 4. Similarly, the integral scale and the Taylor microscale L lambda can be related, L naught by L lambda can be related using the RE defined based upon the L naught and to the power of 1 by 2. So This is a very important thing, and also we will see that based upon the length scales, we will be able to characterize the turbulence for turbulent mixing premixed flames. Now, turbulent stresses. So, you know the stress terms. Normally, we know in flow field there are stress terms: normal stress and shear stress. Okay, so there are stress terms, but if you see, turbulence actually causes some stress terms, but it's not going to cause a stress term, but we can have a stress term defined by analyzing a Reynolds averaged equations. So, we will come to that here. So, first of all, another important characteristic of turbulent flow is this is 3-dimensional in nature, and it is also time dependent in nature. Why? Because chaotic fluctuations are present. So, that will surely cause fluctuations which cannot be taken as a steady state oscillations. So, that they are going to be time dependent. Then they are 3-dimensional, even though the predominant flow is in say 2-dimension, x and y only, predominant flow takes place, but there will be always oscillation in the third direction. Oscillations cannot be prevented. So, for example, in the 3-dimensional thing, u and v are present in the 2-dimensional flow field, but the oscillations in u dash, that is u dash, oscillations in v which is v dash, and the oscillation in w or the z direction which is w dash will be present. So, here w may be 0, but the fluctuation may not be 0. So, that is the characteristics. Okay, you can see that the third direction the flow field will be there is no mean velocity. I see these are mean velocities. The mean velocity in xy direction may be non-zero, but the mean velocity in the yz direction, the mutually perpendicular direction, can be 0. However, the fluctuating quantity w dash may not be 0. So, that actually leaves the turbulent flow as a 3-dimensional flow. Okay. But anyway, we can neglect that. So, there are simplifications anyway we can do, but this I have to understand. So, the fluctuation may not be too large when compared to u dash and v dash. So, if w dash is much less than say u dash or v dash, then we can neglect w dash, but w dash cannot be mentioned as 0. So, that is the main point here. W dash is not equal to 0. However, w dash may be much smaller than u dash and v dash, so that we can neglect that. Okay. We can say w over at bar, that is the mean value of w is 0, that is possible, but w dash can be negligible, not 0. So, that we have to understand. So, and also I told you the chaotic oscillations will introduce the time dependent nature of the turbulent flow. So, that means if I want to solve the turbulent flow, first of all I have to go for a 3D modeling, then smallest eddy is Colgan's scale, very small eddies are present and the large eddies are present. So, if you want to have a dissolved large eddy, you can go for bigger mesh, but if the smaller eddy, if you want to resolve, say that size itself is say 0.1 mm, I am just giving an example. So, now what happens in that, if you want to resolve that, at least your size will be less than that. Okay. So, at least say 5 times less than that, 3 times less than that, and so on, to actually capture that particular eddy, the fluctuations due to that eddy. So, this means that very small grids are required to resolve the smallest size. Similarly, time scale. So, the smallest eddy's oscillation, largest eddy oscillation, etc., will have different time scales. The oscillations, which are several frequency oscillations are there. So, multiple frequencies are present. So, the time steps also will be multiple, correct. So, we have to use the smallest time step to resolve the multiple time step aspect here. So, time steps are to be small, then we can use we have to use smaller grids to resolve the Kolmogorov scale and so on. So, this leaves that as to when you want to resolve it without any worry about the fluctuating components, then we have to use what is called direct numerical solution, DNS. So, this direct numerical solution basically is not easy to apply for any other scale. So, this can be used only for small scale problems, that is it. If you increase the scale of a problem, this will not work. So that is very important. So anyway, some assumptions and some simplifications have to be made, and okay, if it is not a DNS, how will you proceed with this? So that is what we have to see. Okay, so the possible way to proceed without doing a DNS is called modeling, turbulent modeling. Turbulence modeling. So how will you model the turbulence flow? So this means you don't resolve the smallest eddy size, or the smallest the time step which is required to capture the oscillation and so on. So what we try to do here is, when the variables in the conservation equations of mass, momentum, species and energy are written in terms of mean and fluctuating quantities. So we have already defined it. So for example, V at a particular time instant will be equal to V bar plus V dash of t. So now you take the equation, the governing equation, and substitute for each variable mean quantity plus fluctuating quantity. So that we try to do, and now when I split the variable into mean and fluctuating quantity, then I do a time average. Okay, and this type of process is called Reynolds averaging, and what we end up is with the Reynolds average governing equations. So Reynolds averaging is very important. So that will give you mean quantity based governing equation, and the fluctuating quantity terms will be appearing there, correct? So mean quantity is like a laminar flow solution. So due to the turbulence, the fluctuating quantities will give rise to additional terms. Okay, so when I do the Reynolds averaging, I get Reynolds average governing equations which have mean variables which are solved in a similar manner to the as laminar flow. That it has the same meaning as that of the variables what we use in the laminar flow. However, extra terms come in because of the turbulent oscillations or the fluctuation terms. So these are called the extra terms which appear in the governing equations representing the fluctuating components is called turbulent stress or stress terms, Reynolds stress. Okay, so this is very important. So additional terms appear, those terms are called Reynolds stresses basically, or the turbulent stresses. So let us illustrate this with a small example. Let us consider a boundary type equation. That means I neglect see here. When I invoke this, the gradient in the flow direction is not as high as the gradient in the transverse direction, the y. So if the flow is in x direction, the perpendicular direction y, the flow is not very this, then we can invoke the boundary type of equation. For example, we can say that dou by dou x of mu dou u by dou y x is equal to 0. So this is the equation I take. Now please understand that I mentioned previously the turbulent flow is actually 3-dimensional nature, but why I am using the 2-dimensional here, even though w dash is not equal to 0, but w dash is less than u dash or v dash. So in that case I neglect the fluctuation component of the z direction. So I don't need to use z here, the w or z derivatives of that in this. So when I write the momentum equation in the 2-dimensional boundary layer form, I get this equation. Now I assume the density and the viscosity to be constant here. Okay, so this is another assumption I make. So to just illustrate the Reynolds averaging. Okay, now I take the but I am including the time derivative term. Okay, it may not be, if it's steady, then you can neglect this. Okay, the convection terms, these two are the convection terms. So time derivative of the x momentum rho into u per unit volume plus the convective term here, this is y. Okay, so dou by dou x of rho u plus dou by dou y of rho u v that will be the convective terms, and written in the conservative form. That will be equal to the diffusion term, which is dou by dou y mu times dou u by dou y. So this is the momentum equation which I take. Now what I do is, rho I take as constant, so I don't need to write rho here. So u equal to u bar plus u dash. Similarly, v equal to v bar plus v dash. When I do this and substitute here, okay. So I substitute this u equal to u bar plus u dash, v equal to u v bar plus v dash, and now I take what is called the time averaging. So now take time average to this equation. So if writing in Reynolds decomposition methodology, where I write a variable as the mean value plus the fluctuating value, I complete this equation and take the time averaging of the entire equation. Now please understand that in this case there will be some x derivative of the fluctuations, which is due to this term, the second convective term, second term basically. So now I neglect the x derivative of the terms for fluctuations. So for example, dou by dou x of say u dash etc. is neglected, so that I don't use. So when I use the time average and neglect the x derivative of the fluctuations, then I get this equation. So you can see that the overhead bar represents the mean value, okay. So instead of rho u, I write rho u bar. So time derivative of rho u bar plus dou by dou x of rho u u. So it's the same term here, rho u u comes here, and please understand that there will be additional term which is going to go to the other side basically. Then rho u v of, so here also is y. So rho u v of dou by dou y of rho u v. So here also you get the rho u bar v bar. So that will be equal to the momentum term, that is dou by dou y of mu into dou u by dou y, and the extra term, this is the extra term what we get. Okay, when compared to these two equations, you can see these terms on the left hand side are now common, and left right hand is also common, but I have put a overhead bar here to indicate that I have substituted the mean values here. So but I see that I get an extra term. So this term is called the Reynolds stress term, and that this creates what is called a closure problem, because I have extra term u dash v dash. So how will you resolve this u dash v dash? So that is the closure problem what we have. Okay.